The flashlight weighs less by emitting a beam of light. Therefore, the E of light came from the M of the flashlight, and the ratio is c squared. That's how it's done.
The equation also hinted at the enormous amount of energy contained in even a small quantity of matter.
Suppose I throw a baseball at you, okay, and you catch it. The faster I throw it, the more energy it's got. Now, what about when it's standing still? Well, when Einstein goes through his equations, he finds even when it's standing still, there's a lot of energy in it. And in fact, when you do the equations, it's got an enormous amount of energy in it.
Einstein's discovery was a gigantic leap for science, our first real glimpse into the power of the atom. While scientists were still trying to digest it, our next great discovery sent science reeling yet again. A quantum leap is the very smallest leap possible in nature, but it's proven to be an enormous step in thought. Subatomic particles, like electrons, are able to move from one point to another without ever occupying any of the space in between. An impossibility in our everyday world, but commonplace in the realm of the atom. In the subatomic world, atoms and their constituent parts play by a completely different set of rules from larger bodies of matter. A German scientist named Max Planck described these new rules in what he called quantum theory. And it's our next great discovery.
The quantum theory emerges around 1900 because there was a crisis in physics of monumental proportions.
A crisis?
A crisis. New phenomena were being discovered that violated Newton's laws. Madame Curie, for example, refined something called radium. Radium had this magical property of glowing in the dark. Energy was coming out of nothing. Particles were coming out of nothing. That violated the conservation of energy. Energy was coming from nowhere. Around 1900, people thought that energy was continuous, that you could cut electricity, magnetism, you can cut it into finer pieces without end. And yet around 1900, Max Planck, the great physicist, had the audacity to say that energy occurs in packets called quanta.
Now, why did he say that?
Because if you assume that light comes in these packets, then you could explain all the different kinds of phenomenon that we were seeing, that at the fundamental level, at the level of the atom, there was a quantum effect, that energy was occurring in packets. This also meant, by the way, that matter has wave-like properties.
And this is what we call quantum mechanics?
That's right. Now, that's not the way the universe was supposed to be constructed. The atom was like a bowling ball. How can a bowling ball have wave-like properties? Well, in 1925, Erwin Schrödinger, an Austrian physicist, finally writes down the wave equation governing the electron. This is one of the greatest achievements of the human intellect. All of a sudden, we can now peer into the atom itself.
And so we're talking about atoms are waves, atoms are particles, but there's an uncertainty associated with them, right?
That's right. Then a few years later, Max Born, a colleague of Albert Einstein, made the fateful step. The question was, if matter is a wave, then what is waving? Max Born said, what is waving is the probability of locating it at any given point. We sometimes give our graduate students the problem. Calculate the probability that you will dissolve and you will rematerialize on the other side of a brick wall. Now, that's absurd. How can you wake up in the morning and wind up on Mars? How can you go to bed and wind up on Jupiter? That's crazy. And yet you can calculate the probability of that happening.
It's probably low.
It's very low. You would have to wait longer than the lifetime of the universe. But for electrons, it happens all the time. That's what we call electronics. All the modern marvels of the electronic age and laser beams and microchips ultimately come down to the fact that electrons, you don't know where they are, they can be two places at the same time. How can that be? Two places at the same time. Because you don't know where objects really are. This caused so much problems that even Einstein finally broke with the quantum theory. And he said that I cannot believe that God plays dice with the universe.
With all of its weirdness and built-in uncertainty, quantum theory remains the best model of the subatomic world we have.
ancients asked a fundamental question. What is the universe made out of? They thought it was earth, air, fire, water. But if that's what the world is made out of, then what is light? You can't put it in a box. You can't shake it. You can't touch it. It's ephemeral, yet it's everywhere. Light is everywhere and nowhere. Everyone experiences the epiphany of light. But the question is, what is it? And that has dogged physics for thousands of years.
Dogged physics? Doesn't that just make your day, though? Isn't that a reason to come to the office?
That's right. That's why some of the greatest minds, going back to Isaac Newton, made the first definitive studies on the nature of light. Newton, for example, took white light from the sun, shone it through a prism, and showed that all the colors of the rainbow would come out of white light, showing that white light is really a composite, a sum of red, orange, yellow, blue light.
Didn't he also recombine it?
That's right. He could also show that Roy G. Biv, red, orange, yellow, the violet, could be recombined to create white light. So Newton thought that light was in some sense particulate, little tiny corpuscles, as he called it, made up the stream called light. So we had the first theory of light, the fact that light is based out of particles. But however, there was an alternative theory, a rival theory to Newton's theory, that said that light was a wave. And there was a guy named Young who many years ago was able to show that light had wave-like properties. Think of surfing, for example. Every surfer knows that you could ride on an ocean wave, but if a second ocean wave comes at you from another angle, the two waves interfere, giving you an interference pattern, and then, of course, if you're not careful, you wipe out. Mm-hmm. Well, Young showed this with light. He was able to get light, shine it through a small little pinhole, get another pinhole of light, and have these two waves collide with each other, and there it was, a beautiful interference pattern. So we now had two rival theories of light, the Newton corpuscular particular theory of light, and Young's and others' wave-like theory of light.
Now, Einstein took this the next step.
What Einstein said, and this is the genius of Einstein, he said, perhaps both are right. Perhaps Newton showed us that light has particle properties, and that Young showed that light has wave-like properties, and the two are different manifestations of the same thing. Think of like looking at an elephant. You touch the trunk, you think the elephant is a snake. You touch the legs, you think the elephant is a tree. And yet the elephant is a merger of all these qualities. So Einstein introduced the concept of duality, particle and wave-like duality.
What are we looking at?
Here, we're looking at a helium-neon gas laser. It emits a milliwatt of energy, and it demonstrates that light has both particulate and wave-like nature. Look at this. It really does look like light consists of particles. It's a collimated beam, very, very coherent, meaning that all the waves are vibrating in unison.
If there were waves.
If there were waves. Now it goes through this double slit. And as it goes through the slit, it starts to interfere with itself. Waves start to crisscross other waves to create this pattern. So as we see here, the wave starts to disperse. Now, if waves were nothing but photons, individual particles, this would be a simple red dot. But it's not a red dot. It looks like a wave-like pattern. Mm-hmm. That demonstrates in one experiment both the particle and wave-like nature of light, the duality of light.
It took the combined efforts of three geniuses across 3 centuries to help us understand light as we know it today. Without them, we may as well be living in the Dark Ages. The atom, so small it's hard to imagine. 72 quintillion of them fit into a single grain of sand. Finding out what an atom was made of led to our next great discovery. To get the story, I went to Fermilab outside Chicago and met with physicist John Wormersley.
Even 100 years ago, people knew how big the atom was, and they thought that electrons and protons would be spread pretty much uniformly throughout the atom. And they called this the plum pudding model because they thought of the electrons like raisins in a fruitcake spread throughout the inside of the fruitcake.
In the early 1900s, physicist Ernest Rutherford conducted an experiment to further explore the structure of the atom. He shot radioactive alpha particles at a sheet of gold foil.
And he wanted to see what would happen when the alpha particles hit the gold. He didn't expect very much would happen. He thought most of the alpha particles would carry straight on through without being deflected, without being bent through any large angle.